So last time we were talking about making epoxides, right? And so, right, we had two ways we could do it via SN2 reactions, right? One, we would have a an alcohol and a halide, right? And you would treat it with sodium hydride, and that would make your epoxide, right? Or we could do it from an alcohol and like a tosyl group. Again, treat it with sodium hydride or another base, and that would make our epoxide. Because this is an SN2 reaction, we have to worry if, let's say we kind of switch this around and we have our leaving group on the more substituted carbon, right? It's an SN2 reaction, so it has to go through backside attack, so we would invert the stereochemistry of that leaving group. So here the bromide is back, so the oxygen would have to come from the front face. Same thing with if, let's say we had our oxygen had chirality, right? If we do our SN2 reaction here, I'm not doing anything to the carbon-oxygen bond, so I'm just going to leave that stereochemistry when I make my epoxide, right? I pull the proton off, but I don't do anything to the carbon-oxygen bond, right? So this is what we kind of left off on, right? And the very last thing we talked about was the number of steps it took to make an epoxide from a double bond, right? So if you do the halohydrin, right, where you have a double bond, you have to make your alcohol in your halide. Then you treat it with sodium hydride. That takes 2 steps, right? 2 steps from the double bond. Right? And if you want to do this reaction with a diol, right? If you start from your double bond, you've got to turn your double bond into a diol. So we can use catalytic oxygen tetroxide and hydrogen peroxide, or cold dilute KMNO4, right? And that will make your diol. Then you have to turn your diol into your tosyl group, right? Remember, we use tosyl chloride because tosyl chloride's big and it's going to select to be put on the least substituted oxygen. So in this case, it's going to want to go on the primary oxygen because that's easier to get to, right? So that's how we can kind of differentiate our two oxygens, is just relying on the fact that the tosyl group is going to go to the less substituted oxygen. And then again, we use our base, our sodium hydride, to make our epoxide. Now this is 3 steps from the double bond, right? Now, organic chemists really care about 2 things, right? We care about the yield we get on our reactions, and we care about the number of steps it takes to make something, right? And these 2 things are kind of linked together, right? If you have to do a lot of steps, right? You have to wait for those reactions to be finished, then you have to work them up, then you have to like do the extraction and dry them and all that stuff that you guys do in lab, and that takes a lot of time, right? So the less steps you do, the less time you have to wait to get the thing you actually want. And the yield of your reaction is kind of tied to the number of steps you do as well, right? If you do a reaction if you make something in 1 step and it's 80% yield, great, you got 80% yield making that thing. If you have to make that same thing in 2 steps and each step is 80% yield, by the time you make the product that you wanted, you only got 64% yield of that product, right? So your yields go down as you do more steps, right? Because even if you have a really high yield for a step, like, hey, I got 90%, 90%, and 90% over my 3 steps, great. Now you only have 70% or 72% of your product, even though you got 90 for each step, right? So it would be great if we could make epoxides in a single step, right? Instead of having to do all this stuff to the double bond. And we can do that through the second way to make epoxides, which is olefin oxidation. So this is the one-step method to make epoxides. You start with a double bond and you use an oxidant, and that will make your epoxide. Our oxidant is pretty specific, right? The most common oxidant for this are per acids, right? So a per acid is R, C double bond O, 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 H. So the per in per acid comes from the oxygen-oxygen single bond. That is a peroxy linkage. So like just like peroxide, right? Peroxide is, right, 2 oxygen single bonded together, right? Per acids are, you have what looks like a carboxylic acid, but you have an extra oxygen. You have an oxygen-oxygen single bond. And so that's a per acid. So there are 2 common per acids that get used to make epoxides. The first is this, which is called MCPBA, which is short for metachloro per benzoic acid, right? If it wasn't for the extra oxygen, you'd be able to name that, right? But if it was just metachloro benzoic acid, you'd be like, oh yeah, I know what that is, the biggie. Right? So you have MCPBA, which is what I will most likely use as the oxidant on like an exam or something. Your homework uses a slightly nicer uh, thing, which is trifluoroacetic. So sorry, trifluoroperoacetic acid. So they both have the per acid section. It's just you've changed that R group. So the trifluoroperoacetic acid is slightly less explodey than MCPBA. MCPBA has a tendency to blow up. So you can only buy MCPBA as like a 70% pure, because if it gets much more pure than that, it runs the risk of blowing up. So now 100% you can purify MCPBA to 100%, and I've known people that have done it. They have all of their fingers, to the best of my knowledge. But the trifluoro version is less exploding, and it's just used a little more regularly now. But MCPBA is tried and true, and I'm old. So, uh, so how do these work? So these are our 2 per acids, and basically, if you ever see a per acid, you should think I'm making an epoxide, because basically all they ever do, right? So we have our double bond, we have our say MCPBA, we make our epoxide. Right, so how does this work? What is the mechanism? There's a lot of arrows happening here at once. So this mechanism is basically a concerted reaction. All the bonds are going to form at roughly the same time, right? So you've got your peracid, or MCPBA, and so oxygen-oxygen bonds are really weak, right? So they're easy to break. So what happens is your double bond will attack the oxygen on the end of your peracid and break the oxygen-oxygen single bond. When that happens, these electrons will come over here, making a new carbon-oxygen double bond, push these electrons here to grab that hydrogen, and then these electrons will come this way, I guess, here to make the new bond. So I'm going to number these 1, 2, 3, and 4. Right? So you end up with your epoxide, plus you make benzoic acid. So these two electrons right here, between the two oxygens, they end up being the electrons that make the carbon-oxygen double bond of the carbonyl that you have, right? And these electrons here that are in this oxygen-hydrogen bond basically end up being the electrons that bond your oxygen, that make the second bond on your epoxide. So there's a lot of stuff going on here all at once. The thing that's important to recognize is because all these electrons are moving at the same time, right? There's no time for bond rotation, which means the stereochemistry, like the EZ of a double bond, gets transferred to the epoxide. I'm going to pretend I had enough room. Right? Gets transferred to the epoxide. It's a great use of my space. Good job, man. Could just move that up like an inch, would not have no problems. Right. So what that means is if however the groups on the double bond are arranged when we go into this reaction, they're going to stay in the exact same places relative to each other when we make the epoxide. So, right, so let's say we have a trans slash E double bond, and we treat it with MCPBA. You're going to end up with your epoxide. You're going to have the groups be trans from one another. Those two methyl groups are going to be on opposite sides of the epoxide. If you have a cis double bond, cis or Z, right? And let's say we use like, oops, the trifluoro peracetic acid. Same thing, I'm going to end up with my epoxide, and the two groups that were on the same side on my double bond end up on the same side on my epoxide. Now, this is similar to a lot of the stuff that we've done where we don't know if those two methyl groups are both on wedges or both on dashes. All we know is that they're going to be on the same side. So you could have this, or you could have this, right, where they're both dashes, but they're both on the same side, right? Same thing up here. Right? All you know is they're on opposite sides. What I like to do as like a bookkeeping thing that helps me keep this like straight in my head is I like to say the things on the bottom of the, let's try that again. The things on the bottom of the double bond, I like to think of those as being closer to me. So I like to think of those as being the wedges. And the things that are on the top side of the double bond as you draw it are away from me, so they're the dashes. You don't have to do it that way, but I just think it's easier in my head to keep track of it that way. So let's say we had right. I do want to point out your book will sometimes on like the homework might abbreviate this something like CCO3H. This CO3H, that is accounting for the per acid part of the reagent. So if you see that CO3H, it's just a per acid. They just didn't want to draw the bonds. Right? So if we look at this, we can say, okay, I'm going to have my epoxide in plane, right? And now I'm going to say the isopropyl group and the ethyl group are on the same side. I feel like on the page they're pointing at me on the double bond. So I'm going to have them point at me with wedges. And then that methyl group is on the opposite side of the double bond. So it's going to be a dash. Make sense? There's another way that you can draw this that does the same thing. You just kind of like change your perspective, which is instead of your epoxide being in the plane of the page, you put some of the carbon chain in the plane of the page. So what I like to do is I like to think about it as like, what if we left the ethyl and the isopropyl in the plane of the page? Then we have our epoxide up, and then our methyl group is back. So the isopropyl and the ethyl are still on the same side. The side they're on is in the plane of the page, right? Then you have epoxide sticking out, you methyl group sticking back. It's a little bit less clear that, hey, this isopropyl and this methyl group are on opposite sides because one's in plane and one is back, but it still kind of does the same thing. So you'll see it both ways. I think that this way is just easier, right? Because it just accounts for all the stereochemistry you see on the double bond. No big deal. Right. There's one time or one situation where like drawing it this way I think is easier, and that is when you have a ring. So let's say you've got cyclohexene, you have your I was going to do it wrong again, MCPBA, right? I think it's easier to say, you know what I'm going to do? I'm going to leave my six-membered ring in plane, right? So I'm going to leave these carbons all in plane. I'm going to put my epoxide up, and that's going to push my methyl group back, right? Now, again, we don't know if the MCPBA approached the double bond from the top face or from the bottom. So I could easily draw thinking epoxide wedged, or I could draw the epoxide dashed, and it's the same thing, right? We don't know which one's wedge, which one's dash. We just kind of know where they are relative to each other. That makes sense? So I kind of described this in the previous class as, remember when we did stuff like this where let's say we had, our cold dilute KMNO4, right? We put our oxygens on and we would leave the six-membered ring in plane and just say, hey, the new thing I put on, I'm going to give stereochemistry to, right? That's effectively what we're doing here with the MCPBA or the trifluoroperbenzoic acid. We're just like, oh, I've got a ring. It's easier if I leave the ring in plane, and just the new thing I'm adding, which this time's an epoxide, is going to be either up or down, right? So, and again, we had the same issue where they could both be down or they could both be up. We didn't know which side the reagent came from. So it's basically what we did in organic 1 when we added stuff to double bonds. It's the same principle. Seem good? To make sure this works right in my head. Yeah. Oh, wait, I went this way. Sorry. Figure it out. All right. First one, where everything is on the double bond, is where it ends up on the epoxide, right? Epoxide. I'm going to say the methyl and the ethyl are pointing at me. And I'm going to say the ethyl and the isopropyl are pointing away from me. Okay. Right. Now here, right, we've got to go through all the rigmarole of let's make our halohydrin, right? So we'll say our bromines here, our oxygen will be, I don't want to make our oxygen like this, I guess, right? And then that's going to make our epoxide, right? Where, so it might just be way easier to just be like, you know what, MCPBA, and I want to get to the exact same thing, right? With one less step. One less time you have to do an extraction or use a set toner and all that jazz. So we can make epoxides. We should probably do something with them since we can make them. Kind of seems like a letdown to just like make them and be like, yep, we're done here. So the main thing that epoxides do is epoxides open up. So we're going to talk about epoxide opening reactions. Right. So basically, again, using our simplest possible epoxide here, we're going to add a nucleophile And that nucleophile can end up adding one of two places. We can add that nucleophile to the more substituted carbon of the epoxide, or we can add the nucleophile to the less substituted side of the epoxide. And depending on what reaction conditions we use, we can choose which side of the epoxide we add our nucleophile to. So there are two ways to open epoxides. We can open epoxides under acidic conditions, or we can open our epoxides under basic conditions. Acidic conditions lead to the nucleophile being on the more substituted carbon. Basic conditions end up with the nucleophile being on the less substituted carbon. So let's talk about the acidic conditions in a little more depth. Right. Right, so you're going to have your epoxide, you're going to have a nucleophile, and you're going to have acid. I almost always just write a generic like H+, because it doesn't really matter what the acid is. A lot of times, like if you fill this with an actual reagent, it might be something like sulfuric acid. But I often, like on the exams, it's just going to be like H+. Right? And that is going to end up with your oxygen on the end and your nucleophile on the more substituted carbon. This reaction is an SN1 type reaction, right? So it's going to go through a carbocation. Right? And you're always going to make the most stable cation, right? So you're going to follow the same rules we followed when we did additions to double bonds, right? You're like, oh, I have two options. I'm going to make the most stable one. Right? So the mechanism here, which I should be able to fit, the mechanism is we're basically doing the exact same stuff we did when we did our ether reactions before with acid, right? So you have your epoxide and you have acid, and the lone pair on your epoxide is going to pick up a proton and end up with a protonated oxygen. Now, when we had straight chain ethers, right, we like depending on what was on the ether would determine if we opened the if we broke the bond or not. Here, epoxides are really straight. So do you remember ring strain and angle strain from organic one? He hopes no angle going to be let down. So if you remember, an sp3 hybridized carbon has a bond angle of 109.5 degrees, right? If we think about a cyclopropane, which is the carbon analog of an epoxide, right? Don't forget cyclopropane, you know this, right? Effectively, it's an equilateral triangle, and geometry says, hey, to make an equilateral triangle, your angles need to be 60 degrees. So there's like this disconnect, right? Because geometry is saying make 60-degree bond angles, chemistry is saying make 109.5, right? So I have to bend my carbon bond angles away from ideal. I have to put those bonds closer together, which leads to a lot of strain, right? The epoxide is effectively the same thing, right? I've got this three-membered ring. The bond angles are really far from ideal. So what happens is as soon as I put a proton on the oxygen, the molecule's like, sweet, I can get rid of this stupid ring and I'll make a carbocation. So basically what's happening is you're trading all that ring strain for the carbocation. So carbocations aren't super stable, but the molecule's like, I'd rather have a carbocation than have this ring. So it pops open immediately. As soon as you put something on it, pops open, you make the carbocation. then your nucleophile can add to that positively charged carbon and make your product. Right? So like I said before, we're doing the same thing we did with like double bonds, right? Remember we looked at added things to double bonds and we'd be like, oh, I'm always going to put the carbocation on the most substituted carbon of the double bond. Well, I'm always going to put my carbocation on the most substituted carbon of my epoxide, right? And I'd be like, okay, this is secondary, this is primary. Which one's going to make a more stable carbocation? The secondary one. So I'm going to open that side of my epoxide. So you're always trying to make the most stable carbocation that you can. So you protonate, you pop open the ring, you make that carbocation, and then you add your nucleophile. So I've used like generic nucleophile, but I want to kind of give a list of what are the common nucleophiles for these reactions. Right, so things like water, alcohols, thiols, and then kind of the odd one here is Br minus as a nucleophile. So these three are kind of exactly what you would expect from an SN1 reaction, right? They're weak, uncharged nucleophiles, right? Br minus is kind of the weird one, but basically it just comes from if you have your epoxide and you add HBr, you end up putting a bromine on one carbon and an OH on the other, right? So HBr brought its own nucleophile, right? It's an acid, and it brought its own nucleophile in Br minus. So that's why Br minus gets to be used as a nucleophile. So you're just going to look at your epoxide. You're going to say, hey, I've got water and acid. And you're going to open that epoxide. And when you add water, you end up adding an OH. Okay. You can't tell because both sides have an OH, but right, I made this carbocation. And then I added water to that. Right, I made the most substituted carbocation I could. Do the same thing with ethers. I actually made an epoxide there. Again, add to the most substituted side. I'm going to make that as my product. So I've not put stereochemistry in any of these examples, but if you have stereochemistry, right, so let's say we have, you know, and I add, let's say we do a thiol this time, and our acid, right? You're going to lose the stereochemistry on the carbon that you put the carbocation on. Right. So if you remember, so I'm going to pop this open, right? Right. I didn't do anything to this carbon oxygen bond, right? I didn't break that bond, I didn't do anything to it, so it gets to keep its stereochemistry. But the carbon with the carbocation, right? Carbocations are flat. So you have an equal chance of adding to the top face or the bottom face. So effectively, you end up with no stereochemistry there. You end up basically, you get a racemic carbon. So here, this is racemic. You have a one-to-one mixture of the R enantiomer and the S enantiomer. So I just had you guys like not worry about it, right? This is a really bad H. Let me fix that. H. Cool. Right, so you're going to lose your stereochemistry at whatever carbon you open the epoxide on. You lose any stereochemistry that you had because you go through a carbocation. So far, so good. Make sense? Seem decent? So that's the acidic conditions. The trick to keep an eye on, right, is epoxide, nucleophile acid, right? These are in the reaction at the same time, right? I'm like, hey, the nucleophile and the acid are in there at the same time. You're under acidic conditions, right? That is kind of your cheat. You can be like, okay, that's how I know I have acidic conditions, is they're in there at the same time. Basic conditions, there's a tell for most of them you can pick up on. So for basic conditions, you have your nucleophile, you have your epoxide. Your nucleophile most of the time is charged, and most of the time will have then H plus as opposed to the nucleophile and the acid being in together. What this is signifying is you add the nucleophile, you let it do its nucleophile thing, then you add acid once that reaction is done, right? So then that's going to put your nucleophile on the least substituted carbon, right? So this is now strong and charged, acid added after nucleophile adds to the epoxide. All right. So strong charged nucleophile and the nucleophile ends up on the least substituted carbon of the epoxide. That's because we have an SN and SN2 type mechanism, right? So no carbocations here. We're just going to react. SN2, we're going to have to push the leaving group off. So there's no cations, and your nucleophile always goes to the least substituted carbon. So let's look at the mechanism for this. Super short. Right? Our nucleophile adds, right? So we're doing the same thing we did with breaking epoxides, right? When it was the SN2 type mechanism, right? We just had to decide which side was least substituted, and that's the side our nucleophile added to through, right? We've got secondary and primary. Primary is easiest to get to that carbon, so we're able to add to that side. Now, at the start of this set of slides, I made a big to-do about the fact that O minus is an awful leaving group. And like, you can't have O minus as a leaving group don't have O minus as a leaving group. We've got to do all this stuff to make O minus a good leaving group, right? That carried through from alcohols to here. And now I just have O minus as a leaving group. The difference here is this oxygen is a good leaving group because it's part of an epoxide, right? We have all that ring strain, all that strain energy. And when you add the nucleophile to it, you pop open that ring and you get rid of all that strain that's in the molecule, right? So you're basically, every reaction, you're kind of like balancing, I'm going to say balancing the equation, but not in the way you did in Gen Chem, balancing like an energy equation, where you're like, hey, I've got this epoxide. It's really strained. If I do this reaction, I make this O minus. What is more stable, having the O minus or having the epoxide? And in these cases, it's better to have the O minus than it is to have the epoxide. The O minus is bad, but you're getting all this energy from opening the epoxide that helps offset the badness, the instability of the O minus. So here, instead of like having to like, put a proton on it or like turn it into a better leaving group, it's a good leaving group because it's part of an epoxide. And what's helping it be a good leaving group is you get rid of all this strain. So this isn't like, this is, having the O minus as a leaving group doesn't kind of invalidate everything we did up until this point. It's not like I like lied to you for like 2 weeks. That'd just be weird and mean. It's just that because this is an epoxide, you get to have an O minus as a leaving group, right? So you add your nucleophile, and then after that nucleophile is added, that's when you then add the acid to the reaction at the end, and that lets you don't want an O minus, right? You want an alcohol. So that O minus picks up that proton, and you make an alcohol. So here, you do the whole reaction first, then you add acid at the end. So if you're not 100% sure, like 80% of the time, look for the then. If there's no then, pretty much acidic, and if there is a then, basic. There's one, of course, there's always one sketchy part of it, right? There's always one outlier, right? So what are our common nucleophiles? Right, so let's get rid of just like generic nucleophile minus. What are our common nucleophiles? Again, these are going to fall right in line with the things you would expect from an SN2 reaction from organic 1, right? So you can have alkoxides, you can have hydroxides, you can have cyanides, you can have phthalates, you can have acetylides, so, right, deprotonated alkynes. You can have some organolithiums will work, and some Grignards will work, right? They all end up being like O minuses, right? And these are what you would expect, right? These are your strong charged nucleophiles that you would get from a normal SN2 reaction, right? The outliers, the weirdos, right, are amines. So we can use primary and secondary amines. Right? They're not charged. Amines are inherently basic, and so adding them, you're adding under basic conditions. So the reaction for these is a little different the way you write it up, because you don't have to add acid after the fact to do the reaction with an amine. So let's say again, we have our epoxide, we have our amine, we get our product, right? I don't have the then acid because amines Amines bring their own protons. BYOP. Right? So if you look at this, I have a hydrogen on my nitrogen. In the product, that hydrogen is gone, and now I have a hydrogen on my oxygen. Right? I didn't have to add acid at the end because as I added the amine, the oxygen took the proton off the amine. So this is the one example of it's under basic conditions, but I don't have the then H plus because it brought its own proton with it. Right here, you would just look and say, hey, I've got tertiary carbon, I've got secondary carbon. Secondary carbon is less substituted than a tertiary carbon, so that's where I'm going to do my SN2 reaction. Right? I know I'm under basic conditions because I have the then H plus, and there's my product. Let's talk about the end of basic epoxide openings. So we were doing stuff where we have our nucleophile, right? So we have our under basic conditions, we've got our epoxides, oops, and we have strong charged nucleophiles, and these are all going to add to the least substituted side of the epoxide. So you're going to look at this and you're going to say, all right, I know these are under basic conditions because for the most part, I have the then, right? The then is the tell. The then H plus is the tell, except for when you're using amines. So I know basic conditions. So then you just have to look at your epoxide and decide which of your two sides of your epoxide is the least substituted. In this case, it's the red dot, right? So you've got secondary and primary. Since under basic conditions you're doing an SN2 type reaction, you always just add to the least substituted side because it does the SN2 reaction faster. So we're going to make our product there, right? And we're going to add to the red carbon, and our alcohol is going to be on the blue carbon. All right, so we're going to do the same thing for all of these. So this is a really bad K. So this is SK, right? So again, charged nucleophile, right? The sulfur is negatively charged. I have my then, so I know I'm under basic conditions. And then again, we're going to say, hey, this is secondary. This is tertiary. I'm going to add to the secondary carbon because it's easier to get to, right? Tertiary carbons don't do SN2 reactions. So there's our product. And again, we've got red carbon, blue carbon. And then here, same deal, basic conditions. We're going to add to the red side again. I, for some reason, made the least substituted carbon on the right every time. That was just a fluke. So far so good, seemed pretty easy. So there's no stereochemistry in any of these. So we can go one level deeper and put stereochemistry on them, right? And so there's kind of three versions of this that we have to worry about. We have to worry about stereochemistry on the carbon we don't react with. Stereochemistry on the carbon we react with. And then stereochemistry on both carbons that we react with, or both carbons. So in the first case, we're under basic conditions because we have the amine. Remember, the amines are the ones that have that don't have the then H plus because they bring their own proton, right? So we're going to add our amine to the least substituted side, and we don't do anything to this carbon-oxygen bond, right? Right here, we don't do anything to that. So there's no reason that it would change. So when you have stereochemistry on the carbon-oxygen bond that you're not adding to, you just carry that stereochemistry over into the product. So the stereochemistry right, so the stereochemistry on the carbon you do not react with does not change. Right? So I'm not doing anything to that carbon-oxygen bond, so nothing happens to it. Right? I break this bond, right? I break the bond with the red arrow, but I don't do anything to the bond with the orange arrow, so nothing changes. Now, if the carbon I'm adding to has stereochemistry, this is an SN2 reaction. SN2 reactions with stereochemistry, you always invert your stereocenter. So here, my leaving group is, right, this carbon-oxygen bond. Like, that's my leaving group, is that oxygen. So I have to come from the opposite side of that oxygen to do the SN2 reaction. So I'm going to invert my stereochemistry. Right, so my nucleophile, my hydroxide, comes from behind the oxygen, and that is going to give you inverted stereochemistry. So we're going to invert the stereochemistry. Oops, again. You can invert the stereochemistry at the carbon you react that you react at. So carbon you don't react with keeps its stereochemistry. Carbon you react with inverts its stereochemistry. So if they both have stereocenters, you're just kind of smushing these two rules together. The carbon you react with, you invert the stereochemistry. The carbon you don't react with, it stays the same. So down here, we're going to add to this carbon because it's least substituted. We're going to invert the stereochemistry at the carbon we add to. And we're going to leave the stereochemistry alone at the carbon we don't add to. The question was, does this apply to acidic reactions as well, or just basic reactions? This matters for, this is for basic reactions. Only basic reactions. Remember, acidic reactions, you lose stereochemistry. You keep the stereochemistry where you don't react, but you lose stereochemistry where you do react. Right? So under acidic conditions, let's say we have, kind of same thing, something similar we just had, right? We have this, right? And let's say we have this and H plus, right? The mechanism's SN1. So we're going to pop open, right? We're going to protonate the epoxide. Right? We're going to pop this open to make the carbocation. Right? So when we do that, it's a really bad plus. We do that, there we go. This carbocation becomes flat and loses all of its stereochemical information. It forgets that it was chiral. So you have an equal chance of your nucleophile adding from the top or the bottom. So you just end up with a mixture in the end. So you get a racemic mixture at this carbon. Right? You still don't change anything on the carbon you don't react with. That's consistent. Right? If you're not reacting at that carbon-oxygen bond, that stereochemistry stays the same. But you lose your stereochemistry in acidic conditions. You invert it at the carbon you react at under basic conditions. That all make sense? All right. So there's one kind of like little thing I want to go over, and it's telling the difference between if you added to a ketone or an aldehyde, or if you added to an epoxide. Right? I actually used letters there for you guys. Right? So what I'm talking about is when you look at a product and you have a product that looks like this, where you've added a nucleophile and it's sharing a carbon with your alcohol, versus when you have your alcohol and there's a carbon between the carbon with the alcohol and the nucleophile, right? So a lot of times people have a hard time determining if their starting material was a ketone or an aldehyde or an epoxide. This, right, when the nucleophile added and alcohol share a carbon, a ketone slash aldehyde was added to, right? So this comes from, you have a ketone or aldehyde, you add your nucleophile, they end up on the same carbon, right? Whereas if there's a carbon between the nucleophile added and the alcohol carbon, an epoxide was added to. Right, so here you've got, if I just kind of keep the same thing, right? Here's my blue carbon, here's my red carbon, right? There's an extra carbon between them. So when you look at a product, you can see like, okay, what was my nucleophile? how close is it to the carbon that has the alcohol? And that lets you determine whether your starting material was a ketone or if your starting material was an epoxide or your starting material was an aldehyde, right? So what does this kind of mean practically for you? So let's say you had something where, so you had some sort of synthesis problem and you knew that the product was this, and that you were adding a Grignard reagent, right? You could look at it and say, okay, well, my nucleophile is the negatively charged thing that I just erased from you. The negatively charged thing, right? So it's that, right? That's my nucleophile. That's the thing that's negatively charged, right? Because the metal's plus, the carbon the metal's to is bonded to is minus. So, right, that's my nucleophile. Here's where that nucleophile is in my product, right? It's sharing a carbon with the alcohol. So you know that your starting material, right? You're like, what is my starting material? What is this? You know, your starting material here has to be a ketone because that's the only way you can get your nucleophile on the same carbon as your alcohol. Whereas, let's say we had something similar. We have another organometallic. Right, so you're like, okay, here's my nucleophile. Here's what I'm adding. And so here it is in my product, right there. Now there's an extra carbon between that nucleophile and my oxygen and the carbon that has my alcohol, right? So I've got this extra carbon as a spacer between the nucleophile and the carbon that has the alcohol. That lets you know that, hey, this must have been an epoxide, right? Because my nucleophile isn't sharing a carbon with the alcohol. Right? So we know what our nucleophile is, right? We can find the charge thing. We know that the sodium is plus, the carbon bonded to it is minus. That's our nucleophile. That's right here, right? You can see they're not, the nucleophile is not sharing a carbon with the alcohol. So this must have been an epoxide. Right? Where this carbon right here, like the spacer carbon, is the carbon you added to under basic conditions. And then same thing down here. Here's my nucleophile, right? The benzene ring. Here's my benzene ring. So this was a ketone or an aldehyde. Which was it? Was it did I add that benzene to a ketone or did I add that benzene to an aldehyde? So organometallics plus ketones give tertiary alcohols. This is a secondary alcohol. So aldehydes plus organometallics make secondary alcohols. So this was added to a secondary alcohol. Oh man, I messed up my blue thing. I tried so hard. So just look for those like that tell of like, here's my nucleophile. Is it sharing a carbon with my alcohol? Yes or no, and that'll let you know if you were adding your starting material was an epoxide or if it was a ketone or aldehyde. That makes sense? Seem good? All right. All right. So where do we want to start? Okay, we're going to start at the top. What do we want to do first? So what are the differences between the thing that we're given to start and then the thing after the product after C, right? We've got extra carbons, right? You can see we've got right this right here is this right here, right? So we've got these extra carbons right here that we've got to add. We've got to make a double bond, right? When you have an aldehyde, how do you know how to add extra carbons to it? Just an organometallic with 3 carbons, right? So I've got 3 carbons here. 1, 2, 3. I need to add 3 carbons. So that can be, again, our tried and true isopropyl magnesium bromide. What kind of alcohol am I going to make? Can I make a secondary alcohol? So I'm going to end up with an alcohol here. How can I make that double bond? So turning an alcohol into a double bond. I'm going to suggest we use the one that doesn't make carbocations. We don't have to worry about rearrangements. Give me a P. P. Give me another letter. Letter. POCO3. And then there's a base that has to be with it. Do you remember the base? Pyridine. Yep. There we go. What I'm going to do here, I'm going to add a methyl group. That way, we only ever make one product here. Be fun. I was starting to feel guilty. It's like, oh, we can make 2 products. Let me add a methyl group real quick. There we go. Okay. Now, I've got to get from the double bond to this alcohol and this ether. How could we do that? How do we know how to make products that we end up with an alcohol and an ether? What thing do we start with? What functional group do we start with? Could be the functional group you've been using repeatedly for the last part of the lecture. Is it epoxide, right? So how can I only have one spot, right? So I have my epoxide is going to go right here. So I only have one step to make my epoxide. How do you make an epoxide in a single step? That's right, MCPBA. Right, or there's the other per acid, which I'll just throw in here in case, just to remind you, is trifluoro per acetic acid. Right. Either one of those is going to turn your double bond into an epoxide in a single step. So how do I turn E into the given product? Right. So am I going to be adding my nucleophile to the most substituted side of the epoxide or the least substituted side? I guess what is my nucleophile? Right. My nucleophile is this. Right. This is what's new. Right. Because this oxygen right here, it's already in my molecule. Right. So am I adding my nucleophile to the most substituted side or the least substituted side? Most. So how do I do that? Is that acidic conditions or basic conditions? I could get everything down to the SAT dream of just like a coin flip. And then everyone's just like, no, I'm good, thanks. It is acidic conditions. There we go. Right, so under acidic conditions, you add to the most substituted side of the epoxide. Under basic, you add to the least substituted side. So we're going to have our uncharged nucleophile. Oops, blue again. Have our uncharged nucleophile. And we're going to have our acid. And there you go. So what would we do if we want to put our nucleophile on the least substituted side? This is going to be basic conditions, right? So then it would be a charged nucleophile, then acid. So we can get two different products by just changing the conditions. So that finishes up epoxides. Next time we're going to work our way through carbonyl chemistry. See you then.